Lovely introduction. Oh, actually, I guess I don't need this. I just like reflexively took it. So first, thank you to the organizers for the opportunity to speak here. It's really a pleasure. And thank you to all of you. Yeah, so I'll be speaking about redundancy and implicit regularization in neural network models. So I'm sort of approaching this from the perspective of artificial neural networks, but my hope is that some of the ideas or principles that I'll talk about today will be applicable to a very wide class of models, biological models or artificial models. So I'm hoping that whatever models you study, that you'll find some relevance within this. All right, so neural network models of whatever sort you're interested in often are such that they can represent a wide variety of functions. And so we're going to think of a parameter as specifying a particular choice of function represented by whatever your model is. So for the purposes of this talk, a neural network model is just a parameterized family of functions. So my family consists of a bunch of possible different functions that can be realized. So each particular parameter lives in your space of parameters, and that determines your function, which, so f theta will be a function from whatever your space of inputs is to your space of outputs. Okay. So which function your particular model represents is usually the result of some sort of training or learning process, right? Whatever process calibrates your system to do whatever it is that it's supposed to do. So we can think of this as the output of some sort of optimization algorithm. So the general setup or general framework to sort of solve one of these optimization problems, or in other words, calibrate your system to whatever, do whatever it's supposed to do, is you could just sort of initialize your system at some random parameter and then sort of algorithmically search for the parameter, or equivalently the particular function setting that is best, meaning maximizes or minimizes some fitness quantity. And so whatever this algorithm is, you know, this training or learning process, it will eventually lead you to whatever your sort of observed function is, your observed f theta. So exactly what this algorithmic process is will vary from situation to situation. In artificial neural networks, it's often some form of gradient descent. So gradient descent being you have some way of measuring your error, and you just randomly initialize somewhere in parameter space, and you look around and you figure out which direction in parameter space should I move to make the error decrease the fastest. So move in the direction of the gradient. So in the families of functions that are used in modern AI, there's typically a lot of redundancy. And what I mean by redundancy is that there are different parameter settings that give you the same function. So in other words, so your model is like super capable. It has a lot of potential complexity. And depending on exactly how you sort of jigger it, there's multiple ways to represent one function. So we can sort of formalize this idea using the word fiber. So what I'll call the fiber of a function, and I'll write it as fiber of f, is just the set of different parameters that all give you that function. Said differently, the fiber is the collection of different ways of representing that function. So in whatever system you're thinking about, there's then sort of two natural questions. One is, what do these fibers look like? That is, how can we understand the set of all the different ways your model can represent a particular function? And then given that there is all this sort of redundancy and sort of choice in how to represent a function, what caused whatever process you're using to pick the particular representation that it did? So what causes your training algorithm to select a particular parameter within the fiber and not others? So I'm going to try to dig into this question in two particular families of artificial networks, deep linear networks and feed-forward ReLU neural networks. My hope, as I said, is that even if you're not interested in these particular models, I think that there are sort of ideas in here that hopefully will apply to other more complex models, including ones that are sort of more realistic for neuroscience. All right, so my talk is now going to kind of break down into those two different categories. So I'll start with the deep linear networks. So let me tell you what this class of models is. So your functions are just linear functions. That's the linear part. And the deep linear network is the idea that your linear function is a matrix X, but it's given by a product of other matrices. So my total function X, it's a square matrix. It's a D by D matrix. And I think of this as being a product of, in this case, capital N other square matrices. So this is like some very simple iterative process. You could think of it as layers of a network with no activation, no nonlinearity. It's just like the simplest possible thing. Multiply a bunch of matrices together and get one matrix. So in this setup, the parameter is just the choice of all the different matrices. So I'll use W to be my vector of matrices that are the factors. And so when we do this, it's pretty clear that this family is very, very redundant. Right, so each particular function is a linear function from d-dimensional space to itself. So it's given by a matrix that has d squared entries. So it's a d squared dimensional space of functions. On the other hand, the number of parameters is, well, there's n matrices, each of which have d squared entries. So you have n d squared parameters. So what this is telling us is that there's a huge amount of redundancy in this family. And indeed, in general, like the difference between these two numbers, the dimension of the space of functions and the dimension of the parameter space is, well, that difference. So these fibers, meaning different ways to represent the same function, are really big. And in this very simple model, they're really nice and easy to understand. Well, actually, they're not so simple, but we can at least get our hands around them. So let me tell you a little bit of a sort of a backstory. So so here's a little bit of a backstory. So for each particular vector of matrices, there's a thing that you could compute. So I'm going to call it G. So this thing, G, is a vector consisting of n minus 1 matrices. And so this is what those matrices are. So like the first one is, it's Wn transpose Wn minus 1 transpose Wn minus 1. And that sort of pattern consists, goes all the way down. So each of these is a matrix that's just computed from my parameter. All right. So some quantity that I can associate to a particular factorization. So scholars, researchers, noticed sort of two things. Well, I'm sure they noticed more than two things, but two things that I'll mention right now. So first off, the value of this quantity G seems to matter when you're actually trying to use these to, like, say, match a data set or something. In particular, when when this vector turns out to be just the vector of zero matrices, somehow this seems special. there's a number of papers about this. They call these balanced factorizations, right? So we're thinking about, of all the possible ways to represent a certain product, there's lots of different ways to factor it into matrices. For each of these factorizations, we can compute this quantity G, and ones that for which G is the zero matrices we call balanced. Somehow these seem to be special. I'm not totally familiar with all the literature enough to say exactly in what ways people have noticed these are special, but they have drawn attention. Well, let me delay. Right. I think just so okay, so I don't have a good, so experimentally, the observation that these were special, I think was often that when you actually tried to train a model, it often turned out that the trained function often had a G that was very close to being zero, the vector of zeros. This wasn't really, I think, totally understood.
I was just going to say it seems quite linked to number 2. I mean, number 2 is certainly special.
Yeah.
So maybe this property that is mentioned experimentally in 1 was a consequence of 2.
Yeah. Well, actually, what I want to do is tell you sort of some of my thinking about this, why it's special. But yes, thanks, Maya. So point 2 is that this quantity G is conserved by gradient descent, meaning that if you compute this G at whatever matrix you initialize, whatever vector of matrices you initialize at, and then you do gradient descent, all the sequences of parameters that you pass through will all have the exact same G. So that's a really strong statement about where you can get to by training. It's because if I initialize at a place where the G is some value, and I really want to get to some other place where the G is a different value, it says you cannot do that using gradient descent. So conserved quantities, they're sort of limiting where you can get to. Yeah.
Is it dependent on what you want to optimize, or is it dependent?
No, this is completely independent of the data set. It is independent of absolutely everything.
Independent of the loss function?
Independent of the loss function. I know, it seems hard to believe, right? That loss function doesn't matter, the data doesn't matter. And I'm going to explain why that is. Yeah. Caitlin. For this particular setup where I'm just multiplying a bunch of linear matrices together. That's the setting. Yeah. Yes. Yeah, this is a very, very simple model. Okay. So, right. So why is this? So the fact that this G is conserved by gradient descent, you can actually see it just come out of calculus. And it's not very illuminating. So just pick a loss function, whatever your loss function is. And when you compute the gradient vector with respect to that loss function, well, whatever that is, you can then compute the derivative of this G quantity in that direction. And if you do write down some things involving the chain rule, it just pops out that dg, d gradient vector is 0. It's not illuminating, at least to me personally. So I wanted to understand this better, in a more sort of, I don't know, a way that seemed more geometrically satisfying. Okay, and so then remark 2, I guess I already said this, that conserved quantities limit where you can get to. So what I want to tell you now is some work that's work in progress. And I am hoping to release the preprint on this topic within the next month or so. And this is joint with Govind Menon at Brown. So this theorem has a bunch of parts. I'm going to talk through the parts separately. So first, I'm going to only consider matrices like the product matrix where it's full rank. And the reason is when it's not full rank, the situation just gets a little bit more complicated. But full rank is the sort of generic situation. All right, so the first observation is that these level sets of this quantity G are the smallest manifolds that intersect all fibers orthogonally. So let me draw a picture. So here's my sort of parameter space. I'm envisioning it as two-dimensional. So there's maybe a collection of parameters that form a line, maybe, that all give you the same function. So all these parameters, all these thetas give the same function, f theta. And then for some other function, there's some other fiber. So these are the fibers. Okay, and so when we do our training process, if we're using gradient descent, let's just say we randomly initialize right here. Where can our gradient point, our gradient vector? I'm not even specifying what the loss function is. So the gradient is the direction where whatever loss function it is decreases, well, I guess negative gradient, decreases the fastest. So if all these parameters give you the exact same function, then moving in those directions doesn't change your gradient at all, right? Because it's the exact same function. The error doesn't change. So that means that your gradient vector, regardless of what error function, loss function you're using, what data set it is, no matter, the gradient always has to be perpendicular to fibers. So the observation is that regardless of your loss function, regardless of your data set, the gradient of your loss function with respect to your parameter must be orthogonal to all fibers. Yes, yes, thank you for pointing that out. Yeah. Yeah, right. So what this tells us is that whatever system you're thinking about, thank you, which not necessarily linear, but any system, right? You have this sort of breakdown of your space of functions in sort of two dual fibrations, meaning there's sets where you get the same function, and then there's the transverse orthogonal directions. Right. So there's this sort of dual picture consisting of orthogonal sets. And if we do any sort of gradient descent, we're only ever going to be able to move along these sort of perpendicular fibers. So that's what this first point is saying, is that we can now reinterpret this kind of somewhat mysterious quantity G that I think was first observed as just sort of popping out of the chain rule. We can interpret it geometrically as G is the function whose level sets are perpendicular to the fibers. So this also gives us, well, a way to sort of reconceptualize conserved quantities. So what's a conserved quantity? It's something, it's some function whose level sets intersect all the fibers transversely. Not only transversely, sorry, orthogonally. Okay. Whoops. So, great. So moving on, point 2. Yeah.
What's the definition of small manifold?
So yeah, what do I mean by, so by manifold, I just mean these sets that are perpendicular to the fibers. And by smallest, I just mean that like, I could maybe make this bigger, like, and it would still be perpendicular, but it's like not necessary. Yeah. Yeah, any other questions before I keep going? Okay. Great. So we're starting to like sort of get this picture of our model space as sort of breaking down into these two sort of orthogonal sets of directions, things where the function doesn't change, and then the transverse directions. And we can only move when we're training in the transverse directions. Okay, so now, what's special about these balanced factorizations? So let me just remind you, right? So balanced, whoops, where was it? Right, so it was, here's your matrix, and right, if you have some factorization of your matrix and you just record this quantity. So balanced was when this quantity is, when it's all the zero matrices. So what's special about those? So here's one thing that is special. So the fact is that these balanced factorizations of whatever your matrix is are exactly the factorizations that minimize Euclidean norm on the fiber. So you have all these different ways of representing your function, different ways of factoring it. And for each of those factorizations, you can compute the norm of that vector of matrices. The balanced ones are the ones where that norm is as small as possible. So said precisely, a particular factorization minimizes the norm if and only if this quantity G is the zero vector, meaning balanced. Okay. So this is, we're looking at fibers, right? So these are like my fibers. And we're saying that within a fiber, there's this quantity G sort of differentiates between different points within the fiber. And the one where the G is zero has the smallest norm. So it's already getting to be special in this way. So another way it's special is we can think probabilistically. So this one, this point 2 is sort of geometrically, something about the geometry. Particular representation has smallest norm. Changing our viewpoint, let's think sort of probabilistically. So let's say we have a particular matrix and we want to factor it. And so let's just suppose we draw entries of matrices from some Gaussian distribution, IID. So this induces a probability distribution on each fiber, right? There's like a likelihood out of all the possible ways to factor your matrix, some ways are more likely than others. So it turns out the probability density is highest exactly at these balanced factorizations. So we now have like two notions of special that are coinciding. There's sort of which representation are you most likely to pick? That's the probabilistic interpretation. There's also which one sort of geometrically is special. Yeah. Centered at zero, thank you. Yeah. Yeah.
Sorry, so I'm trying to reconcile your item 2 with the previous observation. You said that in the training, often, the solution converges to one of these balanced ones. So that suggests that within a fiber,
yes,
right, like they're not all equally likely to get hit, right? So you're going towards like a particular point.
Yes.
In the fiber.
Yes. Right. Yeah. Thank you. Yes. Right. So there's this sort of picture where training happens in this space. And actually, I'm going to say this more explicitly later on. But I think what you're identifying is the fact that we can sort of think of training as two pieces. There's the piece that changes the function, and then there's the piece that changes which point within the fiber you pick. So there's sort of these two subflows.
Yeah.
And like you're being pushed towards certain representations by that subflow.
But within the fiber, you can't flow, right? So somehow if you started.
Oh, yes, sorry. Oh, yes, I'm sorry. I think I misspoke earlier when I was saying what people observed, that it converged to things of, sorry, I shouldn't say, right, the G's did not change. That was, I misspoke.
Oh, okay. And then it didn't change when they initialized with.
Yes, sorry, thank you.
Okay.
Thank you for clarifying, fixing my, my misstatement.
So,
Yeah.
So people observe. Sorry. So people observe that the solution satisfies G equal 0, not realizing that it was 0 all the time during the training.
So I can't say, I'm actually not sufficiently familiar with exactly what people know or not, but I just know that there was a sense that G equals 0 happened a lot.
Okay.
And I'm sorry, I can't really say.
Were people observing that in the deep linear network or
Yes.
also in deep networks that are, okay.
Specifically deep linear networks. Yeah.
Did they try to, so am I understanding that this is a result of like initializing with a Gaussian distribution? Then you always, and you almost with high probability, you end up in a fiber that where this G is close to 0.
Yep.
And then it is maintained
Yes.
by gradient descent as you move among the fibers.
Yep. Yeah. Thanks.
Did they try initializing with anything else? If you initialize with something that's not drawn to the Gaussian.
I don't know. I'm not sure about the empirical observations.
I think we shouldn't dwell too much on that. Yeah, so just
let me show you a picture. This is my conceptual picture. Instead of working with matrices, I'm working with 1-by-1 matrices in this toy picture, meaning numbers. So in particular, depth 2. So some number is the product of 2 other numbers. So here's a graphical picture. So W1 and W2. So level sets, we know what those look like. They're curves where W1, W2 is some constant number. And those are drawn in this sort of greenish gray color here. So those are my fibers. So balanced, if you remember what the balanced condition was, it's this. Well, when I specialize to the case of one-dimensional numbers, what this is W2 transpose minus, I should say 0, not 1, equals 0, which turns out to norm of W2 equals norm of W1. So these red lines are the balanced factorizations in this case. And so we can see that the other G's would be these other, like in this case, they're pink. So these surfaces that intersect the fibers orthogonally. So the matrix case is basically just this picture, but instead of being numbers, they're matrices. And so I want to just within this sort of toy picture, restate what I just said. So first, that the balanced factorizations have the smallest norm within the fiber. So indeed, if we look at one of these fibers, these like gray curves, the balanced one, which is the intersection with the red point, is indeed smallest norm. So now point 2, this is the probabilistic thing. Like say you're on a particular fiber, this one, and you're randomly picking a point in that fiber according to a Gaussian distribution centered at 0. Well, if it's centered at 0, right, you're going to be most likely close to the balanced one. Right, 3. Oh, right, just observing that these 2 different collections of objects intersect orthogonally. Okay. So getting back to sort of, I think one of the things Karina was pointing out, that this this pushes you towards balanced factorizations when you're doing training. So if whatever your optimization algorithm is, includes a penalty for norm, it will push you towards these balanced ones. All right, another way they're special is sort of algebraically. So algebraically, these balanced factorizations are also kind of the cleanest or the simplest. And so if you have your product X, the balanced factorizations look like this. And what is it? So you take X and you figure out its singular value decomposition. So sigma is the diagonal matrix. So a balanced factorization is one where the terms are all just the 1 over nth roots of that diagonal matrix with pre and post composition by rotation matrices. So in a sense, it's like you take your matrix X and you sort of split it up into these factors as evenly as possible. And the only thing you can do is just sort of rotate them. Yeah.
Hey, and I'm just checking that like the only rotations that actually matter here are like the first and the last.
Yes.
So everything internal just like cancels.
Yep. Yep. Yeah. And what you're saying is exactly the description of like what's in the what's in the part of the fiber that consists of the balance factor.
Like what's in the intersection.
Yes. Yes.
Is like the only thing that changes is these like what are the internal rotations that cancel out?
Yes. Yeah. And to say it even more concretely, the intersection of a fiber and the balanced manifold is the orbit of a rotation group.
Cool.
So it has this really nice, structure. Okay. So, right. So this is some observations about representations within this particular deep linear network case. So let me try to just pull out some of the overarching ideas, which maybe are already obvious, but whatever your model is, we can think of whatever your training flow is, or algorithm, is happening on sort of two things. There's changing your function, and then there's changing your representation within your fiber. So one could break the question of studying training or model selection into two pieces, selecting a function and then selecting a way to represent a function. So in this very, very simple setting of deep linear models, we see that there's these privileged representations. And in this case, at least three different things coincide. These sort of privileged choices, they minimize norm, they also have a sort of probabilistic interpretation, and they're also sort of the simplest algebraically. So I guess the overall, moral is that your model can have bias towards special ways of representing functions. And so it's maybe helpful to understand the many different ways of this redundancy and think about which ones are special. Okay, so that's the end of like the deep linear network part. Now I'm going to talk about another model, feed-forward ReLU neural networks. So unlike the deep linear networks, which are linear, these ones involve thresholds, which unsurprisingly makes everything much, much more complicated. So, here's the definition of a ReLU neural network. So it is, well, for the experts, the fully connected feed-forward ReLU neural network with ReLU activation function on every layer except possibly the final layer and output in R1. So more concretely, what is it? It's functions that are built as compositions of affine linear maps followed by coordinate-wise application of ReLU. So this is your threshold. ReLU taking the max of 0 and x. So in this case, our parameter space is just all the weights and biases, meaning all the entries in the matrices that determine these affine linear maps. Okay. So unsurprisingly, having a threshold causes fibers to get a lot more complicated. So I want to work through just a couple just really simple examples. So here's a super concrete example. So in this case, we're going to go from R1 to R2 to R1. So these are affine linear maps. They're specified parameters. Specified by parameters, there are 7 of them. So my parameter space is R7. And concretely, here's what the map is. Your input X gets sent to ReLU of AX plus B in the first coordinate and ReLU of CX plus D in the second coordinate. And then your next layer does this. So let's just kind of envision what this looks like. So this is my example down here. Let's imagine we initialize somewhere where A and B are positive. So we can then envision the graph of this first neuron as this little picture right here. So AX plus B would give you a line that looks like this. That is not what ReLU does. It should look like, what have I done? Okay, well, whatever choice of AX, no, that's not possible because that is negative. Okay, imagine A is negative and it looks like this. So you can, yeah, edit this example suitably. We can similarly draw the graph of what the second neuron is doing. And then if we maybe imagine that E and F are positive and G is negative, when we add these together, the graph kind of looks like this. And then the ReLU makes the things that are zero, negative 0. So in total, you get a function that looks like this. All right, so our parameter space had 7 parameters, but we just saw that for, well, whatever the suitable assumptions on what these parameters are, locally, you're always going to get a graph that looks like this. And so there's really only two things that can change. You can change where this bend point is, and you can change the slope of this line. So there's really a 2D space of functions. All right, here is possibly a different example, which if I did it correctly, in this case, A, B positive, yeah, okay, that would give you this, C negative, D, yeah, okay, and then you add them together with positive, yeah, okay, you get something like this. So here, for parameters that are kind of look of this type, we now have, well, there's 2 sort of bend points, and then there's like 2 slopes. Oh, and there's also sort of a vertical offset. So there's 5 things that we can change by perturbing our parameters. There's a 5D space of functions. Right. So what we're observing is that fibers in this setup can have different dimensions in different places. So fibers can have pieces that have different dimensions. Maybe this example doesn't show this, but hopefully you can believe that parameters that are in like really different regions of your parameter space can build the same function in very different ways. This is kind of because the threshold can just like collapse out a lot of behavior, right? So you could imagine that you have these sort of layers that are like building up complexity. And then maybe you have a layer where everything's sent to be negative, and then the ReLU just like zeroes it out. So what that is saying is that those early layers, like what they were doing doesn't matter. It doesn't impact the function. Oops. Yeah, so it's locally or sorry, there's a 2-dimensional space of, or this, yes, so 7, yeah, parameter space is 7, yeah, 5 dimensions of functions, 2-dimensional fibers. In the previous slide, it was 5 dimensions, yes. Yeah, thanks.
I'm just going to suggest if somebody says question, then I'll immediately come with a mic. Yeah.
So we can have, in these different regions, we can have fibers with different dimensions. So another observation is that because of these sort of thresholds, our parameter space breaks up into chambers according to which neurons are like active and not active. And so within a chamber, our map is, we're essentially looking at linear maps. If we restrict our attention to where sort of the pattern of activations is fixed, it's essentially a deep linear network. And so our parameter space breaks up into these sort of chambers. Within a chamber, which is like away from where the chambers meet, fibers are, for ReLU neural networks, manifolds. This just comes from sort of the like Sard's theorem or the implicit function theorem. So here's this is based on joint work with my colleague Ellie Grigsby. So a theorem is that for ReLU neural networks, locally near almost any parameter, your parameter space looks like a product space. It's exactly this picture here. There are fibers and there are orthogonal spaces. And so this is only a local description because there's different regions where these fibers have different, the pieces of the fibers have different like dimensions, and you know, we're not saying anything about where these regions sort of fit together, but within a chamber, you have this sort of picture. So yeah, within a chamber, or almost everywhere, we can think of the parameter dimension as consisting of the functional dimension, like the space of functions, and then the symmetry dimension. So it's the dimension of the fiber and the dimension of the, well, the complement of the dimension of the fiber. So here's sort of my conceptual picture. Globally, our parameter space is a patchwork of these pieces. So functional dimension is what I'm going to call the dimension of the space of functions that you can realize by perturbing a parameter. So like in these previous examples, like this one, I saw that if I perturbed my parameter, I could get a 5D space of functions. So I'd say that the functional dimension of this parameter is 5, whereas the functional dimension of this parameter is 2. So here's a question. Well, okay, I'm getting it. Let me go back. No. So how does this functional dimension relate to this question of which representation you pick? Yeah.
Are you guaranteed that your fibers are continuous?
No, or connected. Yeah. And in fact, they're not in the ReLU setting, or maybe they could be, but at least some are not.
Okay, so you can have discontinuities then.
Yes, yes. And in fact, I think it's likely that's sort of generically the case, that fibers consist of like a bunch of different disconnected pieces, and these pieces can have different dimensions.
Okay, so you really are sort of taking the space, the parameter space, and I'm thinking about it as like a coloring problem now, where you're kind of, you know, each fiber has a color associated to it, and you can then have, it can end up being a quite complicated patchwork.
By a color, you mean like a connected component?
No, I'm thinking about, so right, so Well, no, the like in sometimes, right, the fiber is the set of parameters that give you a particular function.
Yep.
So I can think about that function as a color
Okay.
in the sense of, so
Yeah.
and then I'm going to color my space of parameters.
Yep.
You know, however many different functions are realizable in this parameter space.
Yep.
And what you're telling me is that those colors can be disconnected
Yes.
in interesting ways.
Yes, yes, thank you. Yeah. In fact, the question of exactly what these colors or fibers look like, I think is really not known. Like I can build examples where they're disconnected, but I don't know more about their topology, like, you know, Betty numbers, for example, like, yeah. Right, okay. So let me tell you about a toy experiment. We picked just some network architecture. What this means is that you start in dimension 1 and your intermediate spaces are dimension 15 and you end up at 1. And we picked 3 different toy data sets with complexity at different scales. And what this picture is showing is our toy data sets. So F1 data set is just uniformly sampled points from this blue curve. F2 is green, I don't know if you can see, it's and then F3 is like even another level of complexity. We got these from it's just a Fourier series, or more terms of a Fourier series. So this is we're gonna do a regression task on these 3 different data sets, which are distinguished by sort of different levels of complexity. And the question is, if we use this particular architecture and we do training, so we randomly initialize, we do gradient descent, blah, 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 and we track the functional dimension. So, you know, you initialize and at your parameter, you compute the dimension of the space of functions. And like, as you walk through parameter space, you keep track of that dimension. Well, it'll locally be constant, but when we sort of move from chamber to chamber, this dimension can change because the fiber can have pieces of different dimensions. So let's keep track of that as we do training for these 3 different data sets. And that's what this toy experiment does. So we tracked how the functional dimension evolves when we train for each of these 3 different data sets. So this is the epochs of training across the horizontal axis. And on the vertical axis, we computed, well, an approximation of the functional dimension of the parameter that you're at. And so we did this 20 times for each data set. So just randomly initialized 20 times, did training, tracked it. So what we found is, so F1, that was the simplest data set. If you look at sort of the average of functional dimension over these 20 runs, it's this curve. The sort of medium complexity data set gave you this average, and then the high complexity gave you the green. So what this suggests is that our training process is picking out parameters whose functional dimension reflects the complexity of the data set. So this is in some sense not surprising because you're training your model to do something, and your model, given whatever the situation is, it would like to match that data in the simplest way possible. You know, it doesn't want to have any extra doodads on your functions. It just wants to. I'm assigning emotions, but you'd sort of like to use the minimal complexity representation possible. And so this is suggesting that sort of task complexity corresponds with functional complexity. Yeah.
Okay, so remind me, functional dimension, it's the dimension not of the fiber, of the other thing.
Right, it's
the complement.
Yes, yeah.
Okay.
Here, I'll write that down. So parameter space dimension, param dimension equals functional dimension.
Okay, so the more complicated the
Symmetry.
thing you're approximating, the smaller the fibers, right? You're getting bigger functional dimension for the more complex.
Yes, yes.
Right, so you're getting
yes.
smaller fibers. There's less there's less ways you can do it.
Yes, yes.
Okay.
Yeah.
Okay.
Thanks. I had to like mentally work through the complements. Yeah.
What's the order of magnitude of the parameter dimension? Because it's quite high dimensional space, right?
Oh, you mean the number of parameters?
Yes, the number of parameters.
So my dimensions were, so from 1 to 15, that would be a matrix that's 1 times 15. 15 to 15 would be another 15 squared parameters. I don't know what that is.
Yeah, okay, but it's
thousands?
Yeah.
No, hundreds. Yeah.
It's a big number. So
it's a big number.
Okay, so basically the decomposition is kind of a big number is kind of 30 and then a big number again. So the symmetry dimension is huge all the time.
Yeah. Right, yeah. So kind of simple data sets in some heuristic sense should correspond to simple functions, and simple functions, you should be able to represent them or build them in like lots of different ways, right? Because if you have like a really complicated function, it should be hard, to make to get it. Whereas a simple function, oh, it should be like easy. You can do lots of different things. So this is with a little bit of regularization, meaning penalty on the norm. So kind of as in the DLN example, the idea is that if you put a penalty that explicitly, biases you towards something, in that case, it got to balanced factorizations. This is suggesting that it's at least partially pushing you towards, these lower functional dimension spaces. All right, so I'm almost out of time, which is perfect. So I'm just going to recap. So your model, your neuroscience model, is probably very complicated and probably can represent functions in lots of different ways. This is the fiber. So just to recap, the question is like, why does your model select the particular way it does of representing your function? And so I think there's lots of different ways you could look at this question. The three that I've sort of looked at in these simple models are sort of geometry, probability, and then sort of like algebraic complexity. Right, so gradient flows are orthogonal to fibers. If you're using gradient flow, that'll be the same for whatever model you're using. If it's not gradient flow, you still will have some sort of constraint involving the fiber. And this tells you that the geometry of fibers dictate the possible places you can get to by training. And it also gives rise to these conserved quantities, which are exactly these sort of indexing these orthogonal objects. So I'd like to suggest that it might be useful to think of whatever model you're working with as really sort of your training or stabilization calibration process as consisting of these sort of two pieces, adjusting your function and then adjusting your representation of that function. And the question is like, right, which representations are privileged? Why does your model represent the function it does in the way that it does?
Questions?
What happens with the orthogonality at points where one of the ReLU is 0? Because I think this is where the dimension of the fibers changes, right? So, and what's the gradient doing there?
Right. So ReLU is a little bit persnickety in that it's not actually differentiable everywhere, right? Exactly at where that threshold activates. So technically there is no gradient at points where one of the neurons, changes its sign. So I guess in a sense, gradient flow isn't even defined there. I guess in reality, when you implement gradient flow, we don't actually flow, you take discrete steps. And so you probably step over that boundary. So I guess the answer is, right, is not defined. There is no notion of orthogonality there. Gradient flow isn't really defined, but it's a measure zero phenomenon. And so we're just not going to worry about it. We're going to focus on these sort of open regions where it does make sense.
But so can you say that every time your functional dimension changed, that you stepped over ReLU?
Yep.
Okay.
Other questions? Thanks very much.
Yep, thank you.